In this video, we shall address the issue of integration constant in integration. Let's assume we want to integrate a function f(x) with respect to x. Now this is an indefinite integral because it does not have any limit. The way to express the answer is in a following form. Let's assume the result is another function, gx, and usually we accompany the solution with a constant known as the integration constant. Let's call it c. The question is, how important is this constant? And what does it address? Let's look at some specific examples to address these issues. As an example, let's look at the following integral. Now we know how to solve this. Let's assume that we substitute sine x for u. That means the differential of u is cosine x dx. Now when we substitute this information inside the integral, that integral will simply become u du, which is just half u squared plus an integration constant. Let's call it a. So substituting the expression for u, we get half sine square x plus a, and that's the complete answer. Let's jot down the answer here for future reference. Now let's try to solve this using slightly different method. Now using trigonometric identity, we know that sine x cosine x is just half sine 2x, and we want to integrate that with respect to x. Now you can take the half out. When you integrate sine, you will get minus half cosine 2x. The minus half comes from that constant, plus an integration constant, let's call it b. So the complete answer is 1 over 4, negative 1 over 4 cosine 2x plus b. Let's compare this answer with the one that we obtained earlier. They seem to be different, but in this case, they only differ by a constant, as may be verified by trigonometry. And for that reason, we choose to write the final answer with entirely different constants, a in the first case and b in the second case. So the role of integration constants is just that, to carry that degree of arbitrariness in the solutions. Now let's assume we turn this indefinite integral to a definite integral by putting in limits. The lower limit is, let's say, pi over 4. The upper limit is pi over 2. You will see that by imposing limits and turning the indefinite integral to a definite integral, we no longer need the constants. Let's see what the answer to this integral is by using this form. It simply will be half sine the upper limit squared pi over 2 minus half sine squared the lower limit pi over 4. And that's going to be sine pi over 2 is 1, so that's just half, minus half sine pi over 4 is 1 over square root 2, square that is 1 over 2. So the final answer is 1 over 4. Now let's see what we get if we use this form of the solution. So you will get minus 1 over 4 cosine 2x, 2 times pi over 2 is simply pi, minus 1 over 4 cosine 2 times pi over 4 is pi over 2. Cosine pi over 2 is 0, so that term goes away. Now the first term will be minus 1 over 4. Cosine pi is minus 1, so minus 1. And you get 1 over 4, just like before. So you see that the arbitrariness due to integration constant is eliminated whenever we turn an indefinite integral to a definite integral. Let's look at the second example. We know that when you differentiate hyperbolic tangent of x with respect to x, you get square of hyperbolic secant of x, like that. That means when you integrate hyperbolic secant square x with respect to x, you should get hyperbolic tangent of x, of course plus an integration constant, let's call it c. So one answer to this integral is just that, hyperbolic tangent of x plus an integration constant, let's call it c. One can also obtain solution of another form. If we rewrite the above integral in the following form, secant is just, or hyperbolic secant is just the inverse of hyperbolic cosine. So you get that. Since we know hyperbolic cosine is half times e to the power x plus e to the power minus x, substituting this definition in here, we get 4 dx over e to the power 2x plus e to the power minus 2x plus 2. Let's multiply up and down by e to the power 2x over e to the power 2x. It's like multiplying the whole integral by 1. And you get the following form for the above integral. You get e to the power 2x dx over e to the power 4x plus 1 plus 2 e to the power 2x, which can be rewritten in the following form. E to the power 2x, that's the numerator. The new denominator can be factored perfectly in the following form, e to the power 2x plus 1 squared. You can check for yourself that this term will give you that upon expansion. Now let's use the following substitution to solve this integral. Let v to be e to the power 2x, so that means dv is 2e 2x dx. Upon substituting this information inside that integral, that earlier integral will simply become dv over v plus 1 squared. And this is an easy integral to do, which will give us minus 2 over v plus 1 plus an integration constant, let's call it d. Substituting the expression for v, you get minus 2 e to the power 2x plus 1 plus an integration constant d. Remember, our earlier substitution was v equals e to the power 2x. I have just substituted v in the solution and you end up with that line. So let's jot this answer below on top here, e to the power 2x plus 1 plus an integration constant d. So for the same integral, we seem to have two results. As long as the integral is indefinite integral, namely does not have any lower upper limit, both these forms are acceptable. Now let's put in limits. The lower limit, let's say 1, the upper limit is 3. And let's evaluate this integral using both the solutions. So let's use the first solution. It is hyperbolic tangent of 3 minus hyperbolic tangent of 1, and the c will just vanish because plus c, you see that the c will just get cancelled and the arbitrariness are removed. And you'll get an answer of 0.233460597, for example. Now let's use the second form. It will be minus 2 over e to the power 2x. X is now 3 for the upper limit, so e to the power 6 plus 1 minus 2 over e to the power 2x. X is 1 now, so e to the power 2 plus 1. And that's going to give you the same answer, 0.233 460,597. So you see, integration constants are indeed very important when you're expressing answers to indefinite integrals. But if the integrals that you're evaluating are definite ones, then integration constants are not needed. Thank you for watching.